I am going to solve the basic exercises, and then you can try to solve one. So the first one is this. Following the content in ASCII encoding of an HTTP request, answer the following questions by indicating where to find the answers in the HTTP request. This is really very simple. It's quite immediate. So the HTTP request is a GET, as you can see. It's used to, I can make it a little bit larger. It's used to get a document from an HTTP server. And the first question is, what is the URL of the request? And here, if you remember, the URL is composed by the protocol that is used to make the request. So in this case, we have HTTP protocol. Then you have the name of the host that you are where you are looking for information, where you have the web server you are contacting. In this case, the name of the host is shown here at this point. Okay. We are using HTTP version 1.1, so if you remember, it's compulsory to indicate the name of the host using one header, which is host, and the name of the host is home.dave.polimi.it. Okay. Then you have the identifier of the specific content in the database of the host, so in the file system of the host, and it's Cesana/index.html. Finally, you should also have the port number, okay, but this is can be omitted because when you are using HTTP, the port number by default is port 80. So it is not appearing explicitly, but is there. So the part of the URL is here in the host, part of URL is in the GET header line. Version of HTTP used, this is really very simple. I have already said this. Version is indicated here, is 1.1. The browser requests a non-persistent or a persistent connection. What is the answer? To see if the connection is persistent or non-persistent, it's very simple. There is a specific header. You remember that this is the first line indicates the type of method that is used, that is contained in the message, and then you have a set of lines. Each one is a specific header, which is an expression containing on one side a name of a content, and on the other side a value. So if you look at the headers that are reported here, you have the header that is called the connection. And keep alive means that the connection must be open, remain open. So this means that we are using a persistent connection. Okay? What happens if I don't put this, if we omit this header in this specific request? How will it will be the connection, persistent or non-persistent? No, it will be persistent, because since we are using version 1.1, the default for version 1.1 is persistent connection. If you remember when we did the experiments with the VirtualBox server, when we used 1.1, when we selected 1.1 without specifying any header except the host, the connection remained open. So with 1.1 the connection remained open. With 1.0 the connection automatically closed, because this is the default. However, you can use persistent connections even with HTTP 1.0, or you can use non-persistent connections even with HTTP 1.1. Okay. If you want to modify the default behavior of the version of the protocol, you have to add this header. And if the header is keep alive, it means that you are choosing persistent. If instead is close, you are forcing to be non-persistent. What is the indication of the type of the browser? What is the type of browser? Sorry? Mozilla Firefox, yes. It is in the header user agent. Okay. So this is a very simple exercise. Now we go to something more, say, numerical, and this is the text. So we have again an HTTP connection, and the client, which is here in this cloud on the right, request an HTTP server web page, request to an HTTP server a web page that consists of a base object, an HTML file, and 10 other items. Each object has a size L equal to 200 kilobit, and the connection between the client and the HTTP server is able to transfer information at the speed of 100 kilobit per second in both directions. Control messages used to open a TCP connection between client and server and the HTTP GET message have a length of 100 bits. So here we have the 200 kilobits for the objects and 100 bits for the control messages. Propagation delay is negligible. Calculate the total time to receive the entire web page in the following 3 cases. And these cases refers to the mode by which the connection is operated. So in the first case, the client opens in parallel all TCP connections required to download the web page. And here when we have these connections in parallel, we can assume that the rate for each connection will be equal to the total capacity, physical capacity of the link, that is this one, divided by the number of connections. Then HTTP client opens a single persisting connection to download all the objects in the web page, or the HTTP client opens in series 11 non-persistent TCP connections. These are the three cases. This model, by which when we have more than one TCP connection sharing a common link, is very frequently used. And remember that is always an approximation. Okay? And you can use it only when you are considering the problem at an application at the application layer from point of view. Okay. So here in this simple example, you see that we have identified this specific link with a capacity equal to C. And then you also notice that the host, the client and and the server are not directly connected to the link, but there is a cloud that is a complicated network that we don't know. However, the rate of the connection is fixed by this link. This means that this is the slowest link that the data that are flowing from the client to the server will cross inside these networks. It is called also bottleneck link, because when you have concurrent TCP connections, the actual rate of each TCP connection is determined by the bottleneck link. So the place where data flows more in the most slowest with the slowest rate, and this is due to a property of TCP protocol. And with TCP protocol, the TCP connections basically try to fill up as much capacity as they can. Okay. So if you have more than one TCP connection sharing the same link, and they are all equal in terms of parameters, they will tend to fairly share the link. So each one will have the same final rate. This is why the rate for each connection is given by the capacity of the link divided by n. We will go back again to this concept when we will deal with layer 4, so the transport layer. At the moment, you can take it as a statement. So the statement says that the rate for each connection is the capacity divided by the number of connections. So what happens in this case? We can again use our tool, that is the time diagram. And so now let me change the color. So this is more or less a diagram. Here we have the client and the server. And we have three cases, A, B, and C, as specified there. So in the first case, the HTTP client opens the connections in parallel. Obviously, connections that are opened in parallel are the ones used to download the objects. So first, the client will download the HTTP page, the HTML page. The HTML page will tell the client how many objects it has to download, and then the client will download the objects. But actually here in this specific problem, yes, we have the web page that consists of HTML file and the other objects that are 10, and the size of the HTML page is the same as the size of the objects. This is not the general case, So always check if the size of the HTML page is specified and is different from those of that of the object. So first the HTML page is downloaded, then after analyzing the HTML page, the server can start asking for the other objects. And in the first case, so the HTML client opens in parallel all the TCP connections to download the web page. This means that initially there is a opening of the connection, and then the HTML object is the HTML page is downloaded. Okay. Here the text says that the propagation delay is negligible, but in any case I am drawing the diagrams in a way that there is a propagation delay, otherwise we don't see anything. So first there is the download of the HTML page, which is this one. Okay. And first there is a connection opening. This is the opening phase of the TCP connection. And this is the get, the first get. Okay. So the connection opening requires a message that is sent from the client to the server and a confirmation from the server to the client. Then there is the get message that is sent from the client to the server, and then the server replies with the HTML page. After this, the client is able to download the objects in parallel. So in this case, we have the connection has been already opened, and we are assuming that the connections are persistent. So here you will have the object download. This will be a get to get the object, and then the objects will be downloaded. This part is run simultaneously by 10 processes in parallel. Okay, so you will have 10 connections that are going through this link at the same time. In the second case, we have a single persistent connection to download all the objects in the web page, and here we assume that the objects are downloaded serially, so one after the other. So you will have the same as the beginning, the other case, with this is the opening phase, and then this is the get, and this is the HTML. Then there will be a get, and objects will be downloaded. After the first object is downloaded, you will have another get to download the second object, and so on, until the last object this is object number 1, this will be object number 10. Okay, this is repeated 10 times in series, sequentially. Finally, the last case is the non-persistent case. So you will have opening of a connection initially, and then when you are, this is the HTML download, and then when you are asking for a new object, you have again the opening phase. Okay, so you have another TCP opening phase. Then a get and the object. Okay. This will be repeated 10 times serially. Okay. So what is the final transfer time? So the total time that you have from this instant to the instant when all the page has been downloaded, the whole page has been downloaded in the client. In the first case, you have first of all we have a round trip time. This is so-called round trip time, and is basically the time that it takes to a bit to get from the client to the server and back to the client. Okay. A message that has a negligible length. In this case, since we don't have any propagation delay is negligible, this time is basically the time only due to the transmission times. So you have the transmission of the message, of the opening message from the client to the server, and the transmission of the confirmation message from the server to the client. And here we have that the length of all these control messages is 100 bits. Okay. Then, in the moment when we are in this phase, in all the system we have a single connection that is running, which is the connection to download the HTML file. Okay. So there is no sharing of this link by multiple connections. So all the capacity, the total capacity C of the link will go to that single connection that is running. So we have to consider, to calculate the total time A, we have to consider a small l is the length of the signaling message, a time that is the transmission of the opening message and the transmission of the confirmation message. The capacity is symmetrical here, so the bit rate from client to server is the same as the bit rate from server to client. And this is to take into account the opening phase of the TCP connection. Then we have the get message that is going from the client to the server, which is again a control message, and it's taking again the whole capacity. Then we have the reply with HTML page. So in this case we have capital L, which is the length of the HTML page, divided by C. And this terminates the phase when we have a single connection that is running. Okay. So now we start the second phase. In the second phase, we have actually I forgot one thing. Sorry, I have to delete this. So when the client starts the 10 connections in parallel, it has, however, to open the connections again, because it is opening connections in parallel, so it cannot use the same connection that was used to download HTML. So actually you have again an opening, TCP opening phase. Then there is the get, and then the object is downloaded. Okay. This is what is done in parallel for 10 times. Okay. So now here we have to add to this to the total time only a single time. This extra interval requires to download the objects, while a single time, because they are all downloaded in parallel. Okay. So the time that is taken to download 10 is the same that is taken to download 1. However, in this case, so again we will have the opening phase, the get, and the download of the object. However, in this phase the rate is different. So we have to take into account that we have 10 connections in parallel, so the rate is C divided by 10. It's not C anymore, because the connections are sharing the same link. So here we will have L divided by R plus L divided by R plus L divided by R again plus capital L divided by R. Okay. So this is TCP opening. This is the get, and this is the HTML transmission, and this is the object transmission. Okay. So this is the parallel case. I don't calculate the numbers, but you can do it by yourself. Then we have the second case, that is the persistent serial case. So here we will have an opening phase for the TCP connection, which is done only once. Then there is the download of the HTML file, and then the download of the objects. So the first part is exactly the same as before, and here we have once the connection has been opened, is this TCP, then we have the phase in which all the objects are downloaded. Since the HTML page has the same size of all the objects, okay, it will be always the same interval of time. So we can write L divided by C plus capital L divided by C multiplied 11 times. Notice that here we are using C because there is always a single connection that is going on at each time. Okay. So the link is not shared. Final case, the non-persistent case. So we will have the opening of the connection each time you have to download the object. Okay. So also here we can consider that the HTML page has the same size as the object, and therefore we will have 11 times connection opening plus get plus object download. Also in this case, notice that we have always the full capacity dedicated to a single connection. Okay. This is the get, this is the object or HTML page. Questions? So another exercise that is quite simple. This one. Here we have again HTTP, and we are using a client which is downloading an object at this server. Actually, Bonsai doesn't match with the picture. The picture is AdLab. And we have an HTTP proxy that is used. So the browser, which is here, the A, has an HTTP proxy configured. And we have a first case when the page is not present in the HTTP proxy. A second case in which the page is present, and the third case in which the proxy is not configured. Okay. The question is to identify what are the messages exchanged between the involved entities in a synthetic way. So here we don't need to go into the details of the single messages transmitted. So again, we can use the time diagram. We need 3 vertical lines. And let's start with the first case, that is A. The browser has the proxy configured and the web page is not present in the proxy. This is A, this is the proxy, this is the server. So A will send a GET to the proxy, and the proxy will receive the GET and will try to find the content in the local cache, but the content is not present in the local cache. Okay. And the proxy, this GET has as a URL, a target URL, the target URL that is requested by by the client, so antlab.date.polyme.it. Okay. Then, when the proxy does not find the web page in its cache, it will forward the GET to the final server with the same URL, and finally the server will start sending the content to the proxy, and this is the object for the web page that is found. When the proxy completely has stored the object is sent, it will send back to the original client. Okay. And the message will be of type 200 OK. That is the exchange. The other case is very simple. There is a proxy configured, and the page is already in the cache of the proxy. There will be basically no exchange between the proxy and the original server. Okay. Third case, I continue here. The proxy is not configured, so the GET will go straight forward to the original server. Okay. In this exercise, there are no numbers, but of course, we can do exercises with numbers that specify the time, the transmission time and propagation time of the objects in other exercises. So now I would like you to do exercise number 2. This one. Okay. So here we have another example of HTTP, and again we have the concept of multiple connections sharing the same link. So this is the bottleneck link that has been already identified, and the capacity is 1 megabit per second of this bottleneck link. In this case, you have 2 connections, 2 TCP, sorry, not 2, but 11, oh no, what is it? 9 TCP connections that are going on in during the transfer that we want to focus. So this is our client, this is the server. So this is the connection that we want to characterize. These are the 9 connections are active during the whole phase, okay, during the whole transfer phase. So you have to assume that they are always active. And you have to remember that when we are adopting this model, the capacity of the link that is called the bottleneck link is always evenly shared by all the connections that are going through that link. So the rate of each connection is always equal to the capacity of the link divided by n, and as in the previous example, these R is changes in time, okay, because also n is variable. Why is variable? Because you have these 9 connections that are permanent, and then the connections that we are focusing, that in the 2 cases, A and B, can be a single connection or a set of connections that are opened in parallel. Okay. So in case A, you will always have a single persistent connection. In case B, the client opens in parallel and in non-persistent mode all the TCP connections needed to download the page. The page is composed by a base object, which is the HTML file, and 11 other items. Okay. Here we don't neglect the propagation time, but we know that the round trip time is 150 milliseconds. So what is the round trip time? Again, it's the time that takes to go from the client and the server and back when you are considering a transmitted packet of negligible length, so the single bit, let's say. This is another condition that is very frequent in many exercises. The control messages here have negligible length. Okay, so when you are opening the connection, you have exactly a round trip time of time that is taken to open the connection, and the get message has no length. Okay, you can start, and let's see if you find the solution.